Ever slam on your brakes and feel like that bag of groceries in the passenger seat almost takes you for a ride?
Oh, yeah.
Makes you think, huh, like what's the physics behind all that motion, you know?
It's everywhere, really.
Exactly. And that's what we're diving deep into today, the laws of motion.
The rules that govern how everything moves, from a falling leaf to a rocket.
But don't worry, no boring physics lectures here, promise.
We're all about real-world examples and those aha moments, making physics actually interesting.
Right. So to really get this, we got to rewind a bit back in time.
Back to the days of Aristotle.
Aristotle, huh? That philosopher.
Yeah, brilliant guy, but even he had a little trouble with motion.
Really? How so?
Well, he thought that for something to move at a constant speed, you need to constantly apply force.
I kind of see that. Like push a box across the floor, you stop pushing, it stops moving.
Exactly. It seems intuitive, right? But then think about it. What if a spaceship in deep space just shuts off its engines?
Oh, right. It wouldn't just stop. It'd keep going.
Exactly, coasting along at the same speed and direction.
So what was Aristotle missing?
Friction. That sneaky force that always seems to be working against us.
So that box I'm pushing, it's not just my push acting on it, but also the friction between it and the floor, slowing it down.
Bingo. Take away the friction in it. That box, well, it keeps moving with just that one initial push.
Forever.
Forever. And that brings us to Galileo. He really challenged Aristotle's ideas.
Oh, yeah, Galileo. He loved those ramps, right? Those inclined planes.
Inclined planes. He was all about those, yeah. He saw that when you roll a ball down a ramp, it speeds up. Roll it up, it slows down.
Right, makes sense.
But what if you rolled it on a perfectly horizontal surface, like no friction at all?
I'm guessing it would just keep rolling.
Yeah.
At the same speed.
You got it. That's how he figured out that an object in motion stays in motion at a constant speed and direction, unless a force acts on it, you know?
The law of inertia.
You know it. Revolutionized how we think about motion.
So it's not about needing constant force to keep moving, but forces are needed to change the motion, like speed up, slow down, or change direction.
Exactly. That's the key takeaway here. Whether an object is at rest or moving at a constant velocity, it really means the same thing, zero acceleration.
No change in motion, gotcha.
And that's where our main man, Sir Isaac Newton, comes in.
Newton, yeah, the guy who gave us the laws of motion.
He built on Galileo's work, you know. So Newton's first law, it's basically like a refined version of the law of inertia, stating that objects tend to resist changes in their motion.
So like a book just chilling on a table stays put, not because there are no forces, but because the forces acting on it are balanced.
Perfect example. Gravity pulling it down, the table pushing back up with an equal and opposite force.
Balanced forces, no change in motion. Got it. So what about when forces aren't balanced?
That's where Newton's second law comes in. It tells us how much an object's motion changes when a force acts on it, like how much oomph it has. Yeah, like think about momentum. It's basically how much oomph an object has.
Got it. So a heavy object moving fast has a lot of momentum.
Exactly. And a light object moving slowly, well, not so much. Newton's second law basically says the force applied is directly proportional to the rate of change in an object's momentum.
Meaning a bigger force equals a bigger change in momentum.
You got it. And it's not just the size of the force, but also the time it's applied over. Like imagine a car accelerating. The engine provides force, and the longer that force is applied, the faster the car goes.
Because its momentum keeps increasing, right?
Right. And the same thing with brakes. Slamming the brakes means a quicker decrease in momentum, bringing the car to a halt faster.
So momentum is a key player here.
Definitely. And it leads to a really cool idea. Conservation of momentum.
Wait, so motion doesn't just disappear?
Nope. It just gets transferred. Like think about billiard balls colliding. One stops, but the other starts moving. The total momentum stays the same.
Makes sense. So we have inertia, the force-momentum link, and now momentum conservation.
Pretty neat, right? And to wrap it all up, we got to talk about Newton's third law.
Oh yeah, that every action has an equal and opposite reaction thing.
That's the one. But it can be tricky. It's not about cause and effect, but more about simultaneous forces.
Simultaneous. Like if I push a wall, it's not that my push causes the wall to push back, but they happen together.
Exactly. It's all about that interaction, the forces existing as a pair.
Whoa, that's deep.
And it's everywhere. From the ground pushing up on you as you walk to the sun and Earth pulling on each other. We'll dive into those examples later, but for now.
Wow. Aristotle to Newton, we've covered a lot about the basic principles of motion.
Yeah, but the real fun starts when we apply these laws to the world around us.
Can't wait.
Me neither.
Back again. Last time we went from Aristotle's early ideas all the way to Newton's laws of motion.
And now,
Now let's see how these laws play out in like everyday stuff.
let's talk friction.
Friction, huh? I always thought of it as like the enemy, makes things harder.
Right. It's everywhere, that's for sure.
But it's also, well, it's essential.
Absolutely. Think about it. Imagine walking on a surface with zero friction, like a sheet of ice.
Oh, I'd be slipping and sliding everywhere.
Exactly. Total chaos.
Okay, yeah, I see how friction helps us get a grip. But it still seems like it makes things tougher, like pushing a box across the floor or wear and tear on engines.
You're right. It can be a pain in those cases. But to really understand friction, we got to dig a little deeper.
Okay, deeper we go. So what is friction, really?
It's not just about opposing motion. It's a component of the contact force between two surfaces.
Contact force, huh? Always kind of threw me off.
Yeah, it's basically whenever two objects are touching, they're pushing on each other. Like you press your hand against a wall.
Right, you push, the wall pushes back.
That's the contact force.
Okay, I see that. But where's the friction in all this?
So within that contact force, there are two parts. One part is pushing the surfaces apart, perpendicular to each other, preventing objects from passing through each other. That's the normal force.
Like a book on a table.
Exactly. And the other part that acts parallel to the surfaces, that's a friction.
So friction is always there, but we only notice it when things try to slide past each other.
You got it. And that brings us to the different types of friction.
Different types. Like what?
There's static friction, that's what stops things from moving at all. And then kinetic friction, which kicks in once things are already sliding.
Yeah. Static and kinetic. Heard those terms before.
Okay, so picture that heavy box again. You push gently, it doesn't budge. That's static friction, pushing back just as hard.
Until you push harder and overcome it.
Right. And then boom, the box starts moving and kinetic friction takes over, trying to slow it down.
So it's usually easier to keep something moving than to start it moving.
Exactly. Objects at rest like to stay at rest, thanks to static friction. But once they're going, well,
Inertia takes over.
you got it. Now, we often see friction as something to get rid of, like oiling up parts in a machine or streamlining a car.
Makes sense. Less friction, things run smoother.
Right. But imagine a world with no friction at all.
Like that ice rink, but everywhere.
Exactly. Sounds fun, maybe, but also super dangerous.
Yeah, I wouldn't be able to walk or hold anything.
Exactly. Friction, even though it can be annoying, it lets us walk, drive, write, even hold a cup of coffee without it slipping.
Starting to see the good side of friction now. But doesn't it go even deeper than that? Like, what causes friction?
You're right. At the microscopic level, friction, tension, all that stuff, it comes from electromagnetism.
Electromagnetism. Sounds like something out of a superhero movie.
Maybe, but it's how our universe works. Friction comes from those tiny electromagnetic interactions between atoms and molecules when surfaces touch.
Like trying to push two magnets together, the same poles repelling each other?
That's a great way to think about it. And how strong that force is, well, it depends on the materials, how rough the surfaces are, things like that.
Wow. So friction, tension, all these forces, they all come from this one fundamental force, electromagnetism.
Yeah, pretty cool, huh? We've just scratched the surface of friction. There's a lot more to explore.
Let's keep going then. What else is there? All right, we're back. We've talked about the laws of motion, dove deep into friction.
And now it's time to put it all together, see how this stuff works in the real world.
Okay, so where do we start?
Let's start simple. How about a pendulum?
A pendulum.
Really?
Seems kind of basic.
Right. But it's in that simplicity that you see the beauty of physics, that back and forth swing.
Yeah, okay, I can picture it. The weight swinging down, then back up. Why does it do that?
So at the top of the swing, the bob, that's the weight. It's like momentarily still.
Right.
But gravity is pulling it down, turning that potential energy into kinetic energy.
Like a skier going downhill, picking up speed.
Exactly. Then, as it swings back up, gravity's working against it, slowing it down, turning that kinetic energy back into potential energy.
But why doesn't it just stop at the top?
Because of inertia. It wants to keep moving, so it overshoots, swings back down.
Ah, that back and forth dance between gravity and inertia.
And that's how pendulums work. And guess what? That same principle has been used to keep time for centuries.
Amazing how something so simple can be so powerful.
It is. But let's switch gears now. Something a bit more explosive. How about a rocket launch?
Now you're talking. Seeing that massive rocket defying gravity is just awesome.
Right. And it all comes down to Newton's third law. Every action has an equal and opposite reaction.
So in a rocket launch, the action is those hot gases shooting out the bottom.
Exactly, with immense force.
And the reaction is the rocket being pushed upwards.
Bingo. It's not pushing off the ground, but those gases.
Oh, I never thought of it that way.
It's like one of those inflatable toys at a water park. You sit on one end, your friend jumps on the other, and you go flying.
Yeah, I see it.
Same idea, just, way bigger and with fire.
So these laws, discovered so long ago, are still behind some of the coolest stuff we do.
It's crazy, right? They're not just some formulas in a textbook. They're the language of the universe.
Speaking of the universe, these laws, they don't just apply to things here on Earth, do they?
Nope. Think bigger. Planets orbiting stars, galaxies colliding.
Even the universe expanding, it's all governed by the same laws.
You got it. From tiny particles to giant galaxies, it's all connected.
Wow, that's incredible to think about.
It is. And that brings us to the end of our deep dive into the laws of motion.
We've come a long way, from Aristotle to Newton to rockets and the universe.
It's all about looking around and seeing those invisible forces at play. That ball rolling, that car turning, even just standing still.
It's all physics.
Exactly.
Yeah.
So next time you see something moving, think about those laws. The universe is full of wonders.
It really is. Thanks for joining us on this deep dive, and keep exploring.